Welcome, everyone. In this talk, we're going to take a look at how you can speed up your Lakehouse query using multi-modal indexing, Subsystem with Presto and Hudi. So today's agenda, we'll start by describing the origins of Hudi that brought transactions, updates, and deletes, and incrementals. Then we'll discuss Lakehouse constituents and how Hudi presents like a cohesive platform for you. In the next section, we can look at how to unlock your query performance using a couple of Hudi's latest features. In the end, we can go through like a benchmarking, which we did with Presto and Hudi to show you how you can materialize your optimizations. So it's good to understand how it all started. Uber back in 2016 was in hypergrowth mode, predominantly HDFS or cloud storage. Everything was immutable. Uber had a core trip database where all trips information was stored. Every 8 to 10 hours, entire data set was ingested to compute your raw tables, and it will also trickle down to your downstream ETLs. As you could see, the entire data set was like a few hundred terabytes, even though your actual change is only like few hundred gigabytes. As you could infer, there's quite a lot of drawbacks in this approach. Ingestion performance was pretty bad, a lot of wasteful resources being used, resulting in a lot of cost to your AWS or whatever cloud storage you're using. And there's no isolation or transactional guarantees for your reads and writes. So Hudi's data lake was introduced to solve the problem. Hudi added like a database abstraction layer to your cloud storage by decoupling your storage and compute. Record level updates were actually supported. Incremental processing was pioneered, which was never heard of before. So with Hudi's data lake, now you could actually just consume few hundreds of GBs at Uber scale every 10 to 15 minutes, rather than trying to ingest 120 terabytes every 10 hours or half a day once. All this was done by ensuring it's transactional, which means that if your writes are actually going through, none of your readers will actually see any of your writes. If your writes fail midway, your reads are never impacted whatsoever. That's how Hudi's journey started with Uber to solve one of the major issues that everyone at the enterprise back one was dealing. That said, we have come a long way from those beginnings. Thanks to the power of the community, it led to where Hudi stands as of today. Let's take a look at how Hudi fares as of now. So Lakehouse has been like an architecture or like a term which has been popularized by Databricks in the last 1.5 to 2 years. So what exactly is a Lakehouse? As the name suggests, it's an amalgamation of data warehousing and data lake in one framework or architecture. OK, it's still abstract for me. OK, let's get into specifics. What exactly can you expect from a Lakehouse? Yeah, so it should be capable of supporting transactional reads and writes. No dirty data or partial reads should be exposed to your readers. It should be capable of supporting diverse kinds of workloads, ranging from batch to streaming, to immutable, or let's say CDC kind of data. You don't want to have like a Lambda or Kappa architecture where you maintain one system for batch, another system for streaming. It should have a rich query engine capabilities or BI tooling, because that's where most of the use cases are going to end up using data lakehouses. Your storage and compute should be decoupled so that you can scale each of them individually and reduce the cost as well. It should have a rich metadata layer with a lot of indices built in so that your reads and writes can be as performant as it could be. So, yep. So let's take a look at Hudi's platform, how it fares well in the Lakehouse architecture. So at the bottom, you have the Lakehouse storage. It could be S3 or HDFS or any of your choice. And then on top, we have like a table format. OK, yeah, so you have an open file format, which is Parquet, Avro, H-file. And then we have table formats, which is like a bunch of files, schemas, partitions, and so on. And then you have a rich set of table services that Hudi offers. Some of them are meant for optimizing your storage layout. For example, clustering is you can reorganize your data based on your query predicates. Compaction is specific to one of the table formats in Hudi, which is called merge on read, where you compact your data in a more optimized fashion so that your read queries are faster. And cleaning is actually meant for reclaiming your space for older versions. If you want to maintain n number of versions of data in Hudi, cleaning is what actually will reclaim your older versions. Next comes the indexes. So index has been there with Hudi for a long time. Even from the beginning, we had like Bloom filter indexes, H-based indexes. These are actually, until recently, mostly it was mainly leveraged on the write path to reduce your write latency. But in this year, we have started putting out a lot of indexes on the read path as well so that you can make an improvement, reduce your read latency as well. So concurrency control. So if Hudi actually supports various different concurrency controls. For multi-writers, we do support optimistic concurrency control. For the table services, which we touched upon, we do support multi-version concurrency control, which is completely non-blocking as well. So think of it as like your regular ingestion is going on, and then you want to compact in an asynchronous background fashion. So none of your ingestion need to actually stop, or there's no downtime required. Your background services can keep on going. Or in another typical fashion, if you have a regular ingestion going on, if you want to backfill to another partition which is not touching your regular ingestion, you can do that with Hudi. So all this, we call it like a transactional or database layer. And then on the top, we have like a execution or runtime. So you have a couple of platform services available to you with Hudi. So for ingestion, we have a tool called Delta Streamer, which is like a self-managed ingestion tool. So all you need to do is connect to your Kafka or let's say S3 bucket, and then it will keep consuming data from there and then ingesting to Hudi. A lot of platform services are available, and then obviously the query engines you can read via Spark, Presto, Trino, and so on. So let's zoom out a bit and see how Hudi fits into an organization's data infra. So you have a lot of different data sources, ranging from, it could be data warehouse, databases, or Kafka, or just files sitting around in S3. You can use Spark or Flink to actually write to your Hudi data lake. And then data lake, as we saw in the previous slide, Hudi comes with a lot of components to actually keep your lakehouse running. So you could ingest into your raw and then have ETL pipelines. So if you're aware of the medallion architecture, the raw is mostly called like a bronze, and then you cleanse your data to build your silver, and then finally you have like a gold tables where your business queries can actually hit through. So, and then in the end, yeah, you have a lot of catalog things, depending on your use case, depending on what query engines you end up using in your organizations, you can do a sync and then try to query, get the querying going. So if you look at Hudi as a platform, gives you most of what you would expect from a lakehouse. So there are two types of table types in Hudi, depending on the workload pattern and so on. It's a lightning talk, so I may not be probably going into details here. So Hudi has been used pretty heavily in some of the larger enterprises, even at exabyte level. There are people using at like a minute level granularity, just to paint a picture of how Hudi has been used across the industry. Our community is pretty large, pretty vibrant as well. So it's come pre-installed with five of the cloud providers. The download stat speaks for itself. Okay, so let's take a look at what are the key components or features that Hudi provides to improve your query latency by an order of magnitude. Okay. Sorry. Yeah. So if you look at what happens behind the scenes while executing a query, the first step involves fetching the metadata, and then followed by query planning, and then applying some optimization, and then eventually reading the data. So metadata fetching is going to be key to improve your performance. Indexes is not something new if you come from a database world. You could have indexes ranging from coarse grain to like a fine grain, depending on your use cases. So as I mentioned in one of the slides, Hudi has indexes on the write path to improve your write latency, so that your merge cost is bounded depending on how much data you write. So we have like an indexing subsystem built within Hudi to make it easier to add any kind of indexes as you want. Recently, we added like a call stats index as well, which is what is going to be one of the future slides which we are going to see. We are adding like a record level index. We are adding like a secondary level index. So the indexing subsystem is built in such a way that the basic foundation is laid out for you. You don't need to worry about how to lay out these indexes, or how to build a new index, how to actually format or organize any of this. All you need to worry about is the business logic behind what goes into the index. Everything under the hood is taken care for you. So even though having a rich metadata, Yeah. Could bring down your query latency unless you optimize your storage catering towards your query predicates. You may not see a major benefit in your query latency. Classical problem, let's say, classical problem everyone will end up is your mismatch between your query pattern and then, sorry, your write pattern and your query pattern. In case of Uber strips data, for example, it's pretty much like date partition tables, but your queries are mostly going to end up reading based on city ID. Sorry about the technical glitch. Yeah, so pictorially you can see that, let's say each color represents a city here. If you don't do any organization to your data whatsoever, a data for a single city is going to be spread across a lot of files. But if you do clustering with Hudi, you can reduce the amount of data scanned. Even though we do leverage the predicate pushdown that comes with Parquet everywhere, the amount of data scanned even before filtering matters a lot. That's why the partition pruning, all those will actually benefit you a lot. So there are different ways to organize optimize your layout. The simpler way is like doing a linear sorting or linear ordering, but there are more advanced technologies that have been introduced by a lot of literature. So Hudi actually added support for 2 of those ones. So these are like multi-dimensional sorting or ordering. If you have multi-field predicates, so you can say that you want to order by, let's say, field 1, field 5, and field 10, which are mostly commonly query predicates in your table. You can add like Z-order or Hilbert. Z-order represents curves in the shape of a Z. It represents in a binary format. It's one of the well-known multimodal index, a way to organize your data. Hilbert is mostly meant for very high dimensional data. Let's say if you have like 10 plus columns that you want to actually organize your data, that's how you can go with Hilbert curves. So let's see how you can leverage data skipping by reorganizing your data in such a fashion. Quick sneak peek into Presto and Hudi integration. So Hudi Presto integration goes a long way. Even at Uber in late 2016 or early 17, when Hudi was introduced, support for read for Spark, Hive, and Presto was there. Initially we had like a Hive connector, and recently we added like a native Hudi connector as well from 2.7.5 in Presto. With the native Hudi connector, we can leverage the metadata table, so the column stats of the data skipping feature, which I'm briefly talking about. There's actually, so we have a latest patch in master, which is going to probably, in the next version, you might be seeing it. So all these are, we could actually get to the Presto users as fast as possible, which was not the case before. Okay, cool. So this benchmarking, we use like a GitHub archive data set worth of 6 months of data, which is roughly around 220 GB with 450 million records. And then we use 3 different flavors to test against the read query latency. First one, no layout optimization whatsoever. The second one is the linear sorting that I mentioned, which is, so for this data set, I use 3 different fields. This is a GitHub archive data set, so I use like a repository ID, the type of the data, and then like a hour of data or something. Yeah. So linear sorting is you sort linearly by F1, F2, F3. Z-order is the advanced methodology that I use. So as you could see here, by organizing your data using these multi-dimensional space filling curves, you could reduce the read latency by like 70 to 80%. It goes hand in hand with your amount of data read, because it organizes the data in a very structured manner so that the amount of data read to actually get to the point that you're interested in is reduced a lot. For example, you see you could see like a reduction of, in some cases, like 95% of data read is actually reduced compared to no data organizing. So a lot of exciting features. I guess we are pretty much towards the end of it. Yeah, pretty happy to take up questions.
Come on, there's got to be questions about Hudi. All right, excellent.
Actually, you talked about the metadata indexing somewhere, and in one of your slides, I saw the Bloom filter index, right? As far as I know, it is probabilistic data structure, and it can show the presence or not present of it. So yeah. How it helps in this scenario, actually?
So as of now, we are leveraging Bloom filter on the write path. So what happens is, let's say you're doing, in commit 1, you're ingesting 1 billion records. In commit 2, let's say you're ingesting only, let's say, 10% of your records, okay? Hudi needs to locate where these records are located. So we don't want to do an n cross m merge on the right path. So we do an index lookup. So for that index, we have Bloom filters for all the data that's been stored. Using that, we build like a interval tree and then try to deduce, okay, where these records are located and which are the new inserts versus updates. That's where we are trying to leverage that. But at the end of the day, yeah, so that will try to reduce, but to confirm that a particular record locates in it's located in a particular file, you need to actually read the file to understand, okay, this is definitely present there.
Okay, got it, thank you.
But we are, as you see here, we are building like a record level index for like a larger data scale. For example, Uber tested like a 10 terabyte record level index, which we are trying to probably come up in the next feature, next release.
Any other questions? Going once? Going twice? All right.